In this video, I'm going to talk about event ordering and mutual exclusion. Event ordering and keeping the clocks in a distributed system synchronized to within 5 or 10 milliseconds is an expensive and non-trivial task. Lamport in 1978 observed that for most applications, it is not necessary to keep the clocks in a distributed system synchronized. Rather, it is sufficient to ensure that all events that occur in a distributed system be totally ordered in a manner that is consistent with an observed behavior. For partial ordering of events, Lamport defined a new relation called happened before and introduced the concept of logical clocks for ordering of events based on the happened before relation. He then gave a distributed algorithm extending his idea of partial ordering to a consistent total ordering of all the events in a distributed system. Happened before relation. The happened before relation denoted by RMR and a set of events satisfies the following conditions. If A and B are events in the same process and A occurs before B, then A goes to B. If A is an event of sending a message by one process and B is the event of the receipt of the same message by another process, then A goes to B. This condition holds by the law of causality because a receiver cannot receive a message until the sender sends it. And the time taken to propagate a message from its sender to its receiver is always positive. If A goes to B and B goes to C, then A goes to C. That is, happened before is a transitive relation. Notice that in a physically meaningful system, an event cannot happen before itself. That is, A goes to A is not true for any event A. This implies that happened before is an irreflexible partial ordering on the set of all events in the system. Happened before relation is continued. In terms of the happened before relation, two events A and B are said to be concurrent if they are not related by the happened before relation. That is, neither A goes to B nor B goes to A is true. This is possible if the two events occur in different processes that do not exchange messages either directly or indirectly via other processes. Notice that this definition of concurrency simply means that nothing can be said about when the two events happened or by which one happened first. That is, two events are concurrent if neither can casually affect the other. Due to this reason, the happened before relation is sometimes also known as the relation of causal ordering. A diagram is often used to explain the concept of the happened before relation and concurrent event states. In the diagram, a vertical line denotes a process. Each dot on a vertical line denotes an event in the corresponding processes, and each wavy line denotes a message that transfer from one process to another in the direction of the arrow. From this space diagram, it is easy to see that for two events A and B, A goes to B is true if and only if there exists a path from A to B by moving forward in time along process and message lines in the direction of the arrows. Logical clocks concept. To determine that an event A happened before an event B, either a common clock or a set of perfectly synchronized clocks is needed. We have seen that neither of this is available in a distributed system. Therefore, in a distributed system, the happened before relation must be defined without the use of globally synchronized physical clocks. Lamport provided a solution for this problem by introducing the concept of logical clock. The logical clocks concept is a way to associate a timestamp with each system event so that events are related to each other by happened before relation can be properly ordered in the sequence. Under this concept, each process PI has a clock CI associated with it and assigns a number CI of A to any event A in that process. The clock of each process is called a logical clock because no assumption is made about the relation of the numbers CI of A to physical time. In fact, the logical clocks may be implemented by counters with no actual time mechanism. With each process having its own clock, The entire system of clocks is represented by the function C, which assigns to any event B the number C of B, where C of B equal to Cj of B if B is an event in process Pj. The logical clocks of a system can be considered to be correct if the events of the system that are related to each other by happened before relation can be properly ordered using these clocks. Therefore, the timestamps assigned to the events by the system of logical clock must satisfy the following clock condition. For any two events, A and B, if A goes to B, then C of A is less than C of B. Implementation of logical clocks. From the definition of the happened before relation, it follows that the clock condition mentioned above is satisfied if the following conditions hold. C1, if A and B are two events within the same process PA and A occurs before B, then CA of A is less than CA of B. C2 is if A is the sending of a message by process PA and B is the receipt of that message by process BJ, then CA of A is less than CJ of B. In addition to this condition, which are necessary to satisfy the clock condition, the following condition is necessary for the correct functioning of the system. C3 is a clock CA associated with a process PA must always go forward, never backward. That is, corrections to time of a logical clock must always be made by adding a positive value to the clock, never by subtracting value. Obviously, any algorithm used for implementing a set of logical clocks must satisfy all these three conditions. The algorithm proposed by Lamport is given below. To meet conditions C1, C2, and C3, Lamport's algorithm uses the rules. Two processes P1 and P2 each have counters C1 and C2. C1 values increase. C1 equal to 0 to 5. C2 values increase. C2 equals to 0 to 5. Counters act like logical clock. Message having the incremented value of counter that is sent by P1. On the other side, P2 receives this message and instead of simple increment of its counter, a check is made. A check is if the incremented counter value of P2 is less than or equal to the timestamp in the received message from P1. If C2 is less than or equal to C1, example 3 is less than or equal to 4, C2 value will be updated with the plus 1. So diagram is shown on the screen. Example for illustrating the implementation of logical clocks by using the counters. As shown in the diagram, two processes P1 and P2 each have a counter, C1 and C2 respectively. The counters act as logical clocks. At the beginning, the counters are initialized to 0 and a process increments is counted by 1 when an event occurs in that process. If the event is sending of a message, the process includes the incremented value of the counter in the message. On the other hand, if the event is receiving of a message, instead of simply incrementing the counter by 1, a check is made to see if the incremented counter value is less than or equal to the timestamp in the received message. If so, the counter value is corrected and set to 1 plus timestamp is received message. If not, the counter value is left as 0. Implementation of logical clocks by using the physical clocks. The implementation is given in the example diagram by using physical clocks instead of counters shown in this diagram. In this case, each process has a physical clock associated with it. Each clock runs at a constant rate. However, the rates at which different clocks run are different. For instance, in the example, when the clock of process P1 has ticked 10 times, the clock of process P2 has ticked only 8 times. Total ordering of events. To satisfy the condition C1, The only requirement is that the physical clock of a process must tick at least once between any two events in that process. This is usually not a problem because a computer clock is normally designed to click several times between two events that happen in quick succession. The total ordering of events. A system clocks satisfying the clock condition can be used to order the events of a system based on the happened before relationship among the events. We can simply need to order the event by the time at which they occur. However, recall that the happened before relation is only a partial ordering on the set of all events in the system. With this event ordering scheme, it is possible that two events A and B that are not related by the happened before relation. It may have some timestamps associated with them. For instance, if events A and B happen respectively in processes P1 and P2, when the clocks of both processes show exactly the same time, both events will have a timestamp of 100. In this situation, nothing can be said about the order of the two events. Therefore, for total ordering on the set of all system events, an additional requirement is disabled. No two events ever occur at exactly the same time. To fulfill this requirement, Lamport proposed the use of any arbitrary total ordering of the processes. Mutual exclusion. There are several resources in a system that must not be used simultaneously by multiple processes if program operation is to be correct. For example, a file must not be simultaneously updated by multiple processes. Similarly, use of unit record peripherals such as tape drives or printers must be restricted to a single process at a time. Therefore, exclusive access to such a record or shared resource by a process must be ensured. This exclusiveness of access is called mutual exclusion between processes. The sections of a program that need exclusive access to shared resources are referred to as critical sections. For mutual exclusion means introduced to prevent processes from executing concurrently within their critical section. Critical section. An algorithm for implementing mutual exclusion must satisfy the following requirements. Mutual exclusion, given a shared resource accessed by multiple concurrent processes, at any time, only one process should access the resource. That is, a process that has been granted the resource must release it before it can be granted. No starvation. If every process that is granted the resource eventually releases it, every request must be eventually granted. Starvation of process. Indefinite postponement of a process because it requires resource, but the resource is never allocated to this process. It is sometimes called live lock. The three approaches to implement mutual exclusion: centralized approach, distributed approach, and token ring approach. Centralized approach. In this approach, one of the processes in the system is selected as a coordinator and coordinates the entry to the critical sections. Each process that wants to enter the critical section must first seek permission from the coordinator. If no other process currently in that critical section, the coordinator can immediately grant permission to the requesting process. However, if two or more processes concurrently ask for permission to enter the same critical section, the coordinator grants permission to only one process at a time in accordance with some scheduling algorithm. After executing a critical section, when a process exits a critical section, it must notify the coordinator so that the coordinator can grant permission to another process. That is also asked for permission to enter the same critical section. The diagram is shown on the screen. An algorithm for mutual exclusion that uses the centralized approach that is described here with the help of an example as shown in the diagram. Let us suppose that there is a coordinator process PC and three other processes P1, P2, and P3 in the system. Also assume that the requests are granted in the first come first served order for which the coordinator maintains a request queue. Suppose P1 wants to enter critical section for which it sends a request message to PC. On receiving the request message, PC checks to see whether some other process is currently in that critical section. Since no other process is in the critical section, PC immediately sends back a reply message granting permission to P1. When the reply arrives, P1 enters the critical section. Centralized approach, the benefits, it is very easy to implement. Requires only 3 messages per critical section: request, reply, and release. Drawbacks in this approach is single coordinator has to handle all the processes, single point of failure, performance down due to bottleneck in large systems. Distributed approach. In the distributed approach, the decision making for mutual exclusion is distributed across the entire system. That is, all processes that want to enter the same critical section cooperate with each other before reaching a decision on which process will enter the critical section next. The first such algorithm was presented by Lamport in 1978 based on his event ordering scheme. Later, Rickard and Agrawala proposed a more efficient algorithm that also requires there be a total ordering of all events in the system. As an example of a distributed algorithm for mutual exclusion, Rickard and Agrawala's algorithm describes. In the following description, we assume that Lamport's event ordering scheme is used to generate a unique timestamp for each event in the system. When a process wants to enter a critical section, it sends a request message to all other processes. The message contains the following information. Number 1, the process identifier of the process. Second, the name of the critical section that the process wants to enter. Third, a unique timestamp generated by the process for the request message. On receiving the request message, a process either immediately sends back a reply message to the sender or defers sending a reply based on the following criteria. Number 1, if the receiver process is itself currently executing in the critical section, it simply chooses the request message and defers sending a reply. Second, if the receiver process is currently not executing in the critical section but is waiting for its turn to enter the critical section, it compares the timestamp in the receiver request message with the timestamp in its own request message that it has sent to other processes. If the timestamp of the received request message is lower, it means that the sender process made a request before the receiver process to enter the critical section. Therefore, the receiver process immediately sends back a reply message to the sender. On the other hand, if the receiver process own request message has a lower time stamp, the receiver queues the received request message and defers sending a reply message. Number 3, if the receiver process neither is in the critical section nor is waiting for its turn to enter the critical section, it immediately sends back a reply message. Distributed approach. To explain how the algorithm works, we can consider an example shown in this diagram. There are 4 processes: P1, P2, P3, and P4. While P4 process is in critical section, processes P1 and P2 want to enter the same critical section. To get permission from other processes, processes P1 and P2 send request messages with timestamps 6 and 4 respectively to other processes. It is shown in the diagram. Now, let us consider the situation. Since process P4 is already in the critical section, it defers sending a reply message to P1 and P2 and enters them in its queue. Process P3 is currently not interested in the critical section, so it sends a reply message to both P1 and P2. Process P2 defers sending a reply message to P1 and enters P1 in its queue because the timestamp of 4 in its own request message is less than the timestamp of 6 in P1 request message. On the other hand, P1 immediately replies to P2 because the timestamp of 6 in its request message is found to be greater than the timestamp of 4 of P2's request message. Drawbacks and solutions. System having n processes. is liable to n points of failure and blocks in case of single process failure. Solution: receiver sends permission denied message when it is in critical section, else it sends OK. If receiver did not receive reply, it keeps on trying after timeout until it gets reply, else it considers that process has crashed. Second, each process must know the identity of process participating in group. When a process joins, it must receive names of all other processes and name of new process must be distributed to all the members of a group. Suitable only for small group due to large number of updates of creation and deletion. Number 3, to much wait if there are large number of nodes. If there are n nodes and single message travels through network, then each process will wait for 2 into n minus 1 messages. It is suitable for small group. Best solution is majority consensus rather than consensus of all processes is proposed in the literature. Token passing approach. In this approach, mutual exclusion is achieved by circulating single token among processes. Token is a special type of message that entitles its holder to enter critical section. Processes are arranged in logical ring structure. Token can be moved clockwise or anti-clockwise. When a process gets token, it can enter critical section, and after finishing the work, it exits from critical section and passes the token to neighbor process. Process can enter critical section one time in each turn with the token. If process not interested to enter critical section, it simply passes token to neighbor. If no one is interested, token keeps on circulating the ring. This is shown in the diagram. The ring topology in the right hand side diagram it is shown. Drawbacks and solutions. The process, first one, process failure. Single process failure causes logical ring to break. The solution is exchange of acknowledgement after message received with neighbor. If no acknowledgement comes, means problem with the process. Current ring information with each process. Using this, each process keeps its faulty neighbor process, and when that process recovers, it informs its previous neighbor or process. And last token. Token is lost. New token message must be generated. Then monitor process and who has token message is lost. The solution is more than one monitor process, and if one failed selection has to be done for selection of next monitor who will generate token. These are all the links are provided to read the algorithm. The video has been provided in this link.